Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everyone. I'm Rustin Leno, and we're going to give you an overview today of work that Jean-Ramon Abrial and I have done in the last 5 weeks on thinking about a hypervisor. So the start of this work came from that when we think about code development today, the typical way that this is done is that you write some piece of code and then you write test cases and you hope that the test cases will work, and you debug the code, and then you find it doesn't really work and you change it, and then of course you leave many bugs in the code and it ships, and you go back and you fix it, and the whole process is very, very expensive. So what we'd like to try to do is to use a different technique for developing code. And the different technique is a top-down technique. So starting from requirements, starting from specifications, and deriving step by step in a gradual way the eventual code. So there are techniques for doing this, and we're using one that Jean-Ramon was a co-inventor of, the Event-B method. And so to have an application for this, to put these techniques into practice, Wolfram Schulte had suggested that maybe we should try a hypervisor. So there was a recent effort to verify the Microsoft Hyper-V. So the Hyper-V is a big body of code, let's say 100,000 lines, and a 3-year project with a joint effort with the University of Saarland. Set out to specify the hypervisor. Now, when you do that, you specify it. So they use the VCC verifier, and when that was specified and verified, that's done after the code is written, and that's always much more difficult. So what we're trying to do here is do all of the specification and so forth up front, so that the code comes last, and that's the top-down approach that we're taking. So. So what we want to do is to produce a hypervisor. So a hypervisor is a virtualizing piece of software that takes one hardware chip with so one physical chip that it wants to virtually give out to a number of operating systems. So each operating system can then execute on this chip as if they had full control over the chip, and we're assuming that there are several cores in the machine, which is realistic these days, and so what we're trying to do is distribute that computation in such a way that when each operating system is running, that is, each guest operating system, as they're called, would not be aware of that the others are running. That is, you cannot detect from the guest standpoint if you're running in the hypervisor, under the hypervisor, or if you're running on the hardware yourself. That's the idea. So that's, for example, what the Microsoft Hyper-V is doing. So that means that there are a number of things that you have to virtualize for these guest operating systems, and the main ones are memory and interrupts. There are also timers and maybe other details, but we're going to focus on memory and interrupt. All right. So the way that the general strategy for doing this kind of work with a top-down development is that we start with a bunch of requirements. So we're going to show you a flavor of the requirements that we write, so the requirements are stated informally, but as precisely as possible, and then you develop some strategy for doing the refinement, which is to say, well, we're going to first introduce the following features, and then we're going to introduce more and more detail into the whole thing. So that's the refinement strategy, and at each step in that living out that strategy is a formal model. So you develop a formal model that describes those pieces of the system that you're building that you're trying to develop at each time. So here, for example, there are choices of which things to introduce first, and as you will see, it comes very naturally to first describe, to start with individual machines that are running, because if you can describe individual machines running in isolation and then refine everything into a system where things share the hardware, then you have from the very beginning proved that you have machines that operate independently of each other. This is also what was done in the or in a similar technique was done in the SEL4 verification project, where they started with some high-level specifications or simulations and tried to refine things. But we're doing it using a different method here, and then we'll conclude. So with that, I'm going to turn it over to Jean-Ramon, who will take us through most of the technical development.
Thank you, Ruston. Good afternoon, everybody. I'm Jean-Ramon Abrial. I'm going to continue. So first of all, we're going to describe the requirement document. We do not rush immediately into the formal modeling. And the requirement document is made of two texts, the explanatory text and the reference text. For the moment, in the requirements we have some sort of short explanatory text, but we put a lot of effort to develop the various reference, and they are made of short statements that are labeled and numbered. So the first task we have to do is precisely for this project to define the values labeled we've envisaged. And here they are. So as Ruston said, we are going first to develop the system independently. So single system memory handling, SM, single system interrupt handling, SI, and then we enter into the notion of multiple system under the control of the hypervisor. So we have a requirement MS, HV for the general requirements for the hypervisor, and then the handling of the memory, which corresponds to this, and the handling of the interrupt, which corresponds to this, and in the middle, the problem of scheduling of the various guests by the hypervisor. Okay, so let's go through these requirements. Because again and again we insist on the absolute necessity to write down very carefully those requirements. So we spend, Ruston and I, a lot of time writing them, and also having interviews and mails and telephone exchanges with some experts, and which gives us some clue in order to understand the problem, because this is their normal job. So here I'm going a little fast through them. You can just read them. So the single system memory handling. So we have an operating system that uses memory device and some timers, and the amount of memory accessible by an OS is determined at boot time, and we call them IPA, intermediate physical addresses. And, by the way, if the OS tries to access memory through a non-existing IPA, then it crashes. That's unfortunate. So the handling of interrupt. So much. There are of course far more things in the handling of the memory for the OS, but we are not. But from the point of view of the hypervisor, we are not interested in that, because this is the private business of each OS. So for the interrupt, we consider only uniprocessor system for the moment. So an OS can be interrupted by some device that are connected to the unique CPU running the OS. And now some properties of the interrupt. Each interrupt has got a priority, which is a natural number. And then we have a notion of state for an interrupt. It could be inactive, pending, or active. And the state of an interrupt is managed by the hardware. So now I'm going to describe a little more carefully these three things and explain with some short statement like this. An inactive interrupt is one that has not happened since it was last treated. A pending interrupt is one that has happened but is not treated yet because its priority it's not big enough. An active interrupt is one that has happened and is either treated now by the CPU or preempted by an interrupt of higher priority, because we can have nested interruption. And now when a pending interrupt is arriving, is defined, if its priority is high enough and it results in the hardware sending a signal and to the concerned core of the OS, and the OS acknowledges signal and the hardware makes the interrupt active. But of course, for a pending interrupt to interrupt an interrupt that is already that is now treated by the guest, by the OS, it has to have a higher priority. So it goes on top of it and becomes an interrupt the interruption. So among the active interrupt, this is the consequence of this thing. The one that is activated is the one that is executed is the one with the highest priority. And here it's a bit redundant what I've said before. A running interrupt can be preempted by a pending interrupt with a higher priority. At the end of the interrupt handling, the OS send an end of interrupt signal to the hardware, which makes the interrupt inactive. So this is a story of an interrupt. An interrupt can be masked or unmasked by the OS. So much for the individual interrupt. Now let's go to the hypervisor requirements. So the role of the hypervisor is to simulate on a single machine with several cores the behavior of independent guest OS. So you can have a look at this drawing here. We have several OS that are independent, and we want to simulate this with the hypervisor. So the hypervisor, as Ruston says, has got as many interrupts as we have here, but you see the numbering is not the same. So these are the physical interrupt, and this becomes, for each individual guest, this becomes the virtual interrupt. And here we have a device, hardware device called the interrupt controller. And here we have, of course, the hypervisor machine has got several CPUs that are connected to the IT controller, and they share a certain memory. So what we have to do is to put all these guys here into this list here, and put all the individual memory here inside a unique memory, so that we can simulate completely with the hypervisor. We can simulate the behavior of several OSs. So we have a number of elements that are determined at boot time. The number of guests is fixed. We cannot add another guest after the boot. And of course, the main thing is that, as Ruston said, a guest OS is not aware that it's been executed on the hypervisor. The guests are rarely independent. This is a very strong requirement. A guest cannot pollute another guest, or cannot, or even don't know that there are other guests. And now, of course, one of the responsibility of the hypervisor is to schedule the guest. The idea here is we might have more guests here than there are CPUs here. So not all the guests are running. So some of the guests might be sleeping. So it is the role of the hypervisor here to, from time to time, maybe some time slice, to eject one of the guests in a CPU and put another guest inside in place of it, if it has been sleeping for a certain time. So you can imagine that there are lots of switching that has to be done when doing this scheduling. And of course, we require here that the hypervisor is fair enough. It's not, from time to time, he has to give control to guests, of course. The hypervisor handling of the memory. So we study two things, as Ruston says. We study the memory first, and then the interrupt. The interesting thing is that for the memory, we go from physical memory to we go from a virtual memory to some physical memory, and for the interrupt, we just go the other way around. So all the memory of the guest are embedded into a single memory, that of the hypervisor. And for making this easy, the hypervisor or the machine here, the hardware, has got a device called the SLAT, the second level address translation, which keeps track for each guest of a one-to-one mapping between each address of the guest and the corresponding address here, between the intermediate memory address here for each guest and the physical address here on the memory of the hypervisor. And this connection is 1-1. This is very important because we do not want for the memories to overlap. So we have this table called the SLAT, and so the things are relatively simple. When a virtual guest wants, for example, to write in his memory, he does not know, but the hardware, the hypervisor, trap this writing operation, and behind the curtain, change through the slats, of course, which is a one-to-one correspondence, which is established at boot time. So through the slats, it translates this IPA, this intermediate address, physical address, into a real physical address. And it is a device that is now in several machines, and which is extremely nice. So the size and content of the slats is determined at boot time, because at boot time we fix completely the portion of the memory of the hypervisor for each guest. So this is determined once and for all at boot time. And again, this is an injective or a one-to-one correspondence, so that the memory do not overlap. The slat itself for each guest is addressed by means of a base address. So for each, there is a slat for each guest, and for each guest there is a base, which is the beginning of the address of the table of the slat. And I will describe more about the slat here. So here, this is a description of what I've just stated, the connection through this map of an IPA to a PA. And of course, if this process fails, then it is because the IPA that has been provided by the guest is a bad one. So we have a second level page fault, and the hypervisor reports to the guest and probably kill the guest because he's trying to access an address that is a faulty one. Okay, and this is described here. Now the slat could be quite big. Therefore, the slat is in fact structured like this here. Rather than having a unique table, it is far too big. So it is in fact controlled by a tree structure of pages. So a PID is a 32-bit address. It has got 10 bits on top, 10 bits here in the middle, and 12 bits on the lower part. We have the base address of a slat for a certain guest. And we have then a top word page here, and then we have a second level, and then a third level. And so the thing is extremely simple. This page here are 2 to the 10 of size, the word page. So the 10 bits here are taken. They address here a certain element in this top page. And then this top page goes on to, this address here goes on to a secondary level a page, which is also a word page. And then we take this 10 bits here, we address here this thing, and this thing here now goes here for the bytes page. Now these are byte page, so 2 to the 12. And this 12 bit here address this, and the memory is here. So the memory of each guest is in this portion. But you see we have these two levels here, or 3 levels, 1, 2, 3, in order to access. Of course, the problem is that, and so this is all explained. In those requirements. So you see, we push the requirement until until this low level. And of course, this is very much time consuming, because you can imagine that in order to go from an IPA to a PA, and the PA is here, the IPA is here, we have to walk through 2 levels. So it means 2 memory accesses, far too much. So there is something called the SLAT, the TLB, the tech, what's the name? Translation lookout buffer. And this is an associative memory, a short associative memory of the size of 16 or 32, and which maps directly a PA to an IPA. So when you walk through this, if it was not in the TLB, then you have the 2, and so you push this into the TLB. Probably you evict some pair of the TLB, and next time, because if we access a memory, we could think that we will pretty soon access the same memory. So then next time, the TLB is doing a short circuit between the IPA and the PA. So this is the technique. So there are lots of hardware doing this. And this is what is explained here. So much for the memory.
So there isn't anything about flashing the TLB? Because I mean, the reason you need to model the TLB is probably because you need to flash it, right? Or, I mean, why do we need to model that TLB at all?
Well, when you're only looking at one machine, then you never need to flush it, right? It's only when you add another machine to flush it.
Oh, that was the single memory. No, that was how I did that. Is there going to be anything about flashing the TLB?
When you flash the TLB, you flash.
When you schedule a new guest operating system,
You flash the TLB.
you have to flash it.
Yeah.
Okay.
You have an individual TLB for each machine, or
For each TPU here, yeah.
for each
core.
For each core.
Which means that the guests and the hypervisor running on that core will have to share it. Will have to share the TLB.
Okay.
I guess I just don't understand why you're modeling it at this level. I mean, if the idea was to come at this top-down level, like even the 3-level mapping, I mean, did you need that at the beginning, or could you just have modeled it? I mean, the point was to model this thing that shares these.
Yeah.
These OSs share the hardware.
This is exactly what we're doing. You will see exactly when I show you the demo. At the top level, at the abstract level, the SLAT is not at all like this. The SLAT is just a, and then we refine, and this is the ultimate refinement. So we go down. Okay, but this is not the first level, of course. But I put it no. But you raise an important point here. The problem is that the requirements are there is some sort of hierarchy in the requirements. Okay, and there are requirements that are very general, and then requirements that are more particular. And precisely this is the role of the refinement strategy, to put this hierarchy and to say, oh, we are going to take this, and then this, and then this, and this in the way we go down. Okay. So, so let's go to the interrupt now. The interrupt was a little more difficult for us because we had to ask the experts, and they give us gradually some information. So the interrupt system of the hypervisor is virtualizing this interrupt. So you remember the situation here. We have the individual interrupt for each TPU, and we have all the interrupt level here for the hypervisor. So first of all, there is a one-to-one correspondence that an injective connection is established between each physical interrupt and a pair made of a guest and an interrupt. For example, the 1, 2, 3 physical interrupt are connected to the 1, 2, 3 of this guest, and then 4, 5 are connected are mapped to 1, 2 of the second guest, and 6, 7, 8 are connected to 1, 2, 3 of the third guest. So and again, this one-to-one connection is established once and for all at boot time. And then each physical interrupt is connected to a single virtual interrupt corresponding to a guest. So now we have the problem that here you remember the interrupt was physically arriving, and here the interrupt will virtually arriving. But what will physically arriving is the physical interrupt. So the physical interrupt arrives here, and immediately the hypervisor traps that interrupt, takes control, and what it does, the hardware put that interrupt as pending, and then the interrupt service routing of the hypervisor takes control, makes the acknowledge the interrupt, and then the interrupt is made by the hardware is made active. So now the physical interrupt is active, but the virtual interrupt is still inactive. It doesn't exist still. So then the hypervisor is looking whether the guest corresponding to this interrupt is sleeping or not. If it is sleeping, the physical interrupt remains active until later on the hypervisor will schedule that guest. But if the guest is not sleeping, for example, that guest here is sitting on this thing here. So what the hypervisor does, it simulates the arrival of the virtual interrupt by sending to some device called the virtual interrupt controller, sending the corresponding interrupt. And the OS is cheated. He believes that this comes from outside. Actually, it doesn't come from outside. It comes from the hypervisor who plays the role of outside. And then things are continuing exactly as I have said. The virtual interrupt is arriving, and now the guest does his own business on this interrupt until the moment where the guest finishes to treat the interrupt. So he sends now an end of interrupt, which is a virtual end of interrupt. It is trapped by the hypervisor and the hardware, which makes this virtual interrupt inactive, and as a side effect, it makes also the physical interrupt inactive. So you see the story of a physical interrupt arriving. So that's more or less what is described here. So now we flew rapidly over the requirements, but again and again, when these requirements are finished, we have something which is clear. We discuss, we send this, we discuss with the experts, we discuss between us, and we thought that now we understand. And now we are ready to do a refinement strategy. So the refinement strategy will follow is the following: handling of the memory, and later on, handling of the interrupts, because the things are pretty orthogonal. And in each case, as Rustin said, we are going to have several physical OS sitting next to each other. So we just formalize this. They are completely independent. They do their little business. And then we refine this by saying, no, this is not true. This was an abstraction, because this is the abstraction we want. We want these OSs to believe that they are completely independent. And then in the refinement, we are virtualizing the OS by means of the hypervisor. And this will take also, as I've said, several levels, in particular for the SLAT, which is not introduced as such at the beginning. So that's what we're doing. Okay, so let me now demo with the Rodin platform. So this is the Rodin platform. So I'm going first to describe the memory. So it's a project called Hypervisor GRA5. You see that there were lots of try before, and eventually we got to this level. So first of all, a project with Event-B is done by a number of contexts and then a number of machines. So the context are the places where the constants are defined. So let me show you the first context. So defining the address space of each guest. We are on each guest independently now. And we have three sets: guest, value, and n. N is an abstract set of abstract state of address. Value is the value to be stored in the memory, and guest are the guest. And there are two axioms and a constant, guest address. So guest address is just the bunch of addresses corresponding to each guest. So it's a set of addresses. And this is not empty. The guest have some memory. Okay, so now we can go to hypervisor M0. So this is the first level. So I explain a bit what has been done here, and also in what I will do in the next one. So the idea essentially is the following: if we take a program trace of an independent guest, from time to time he's writing in the memory. Write A1 V1, write A2 V2, write E3 V3. And in between, the guest is doing whatever he wants on his local problem. But from time to time, he writes in the memory. He also reads in the memory. But we have only considered writing because it's more difficult. Reading is very easy. We have not done it. And here you see this is the corresponding program as executed with the hypervisor. So the hypervisor trap this write operation and change it into an hypervisor write. Hypervisor write, hypervisor write. And what we want to prove, what we want to be sure, is that this program here and this program here are exactly the same. Okay, the fact that this is written now by the hypervisor in this part of the memory here, or in the portion of the memory that is devoted to this guest. So this is essentially what we're doing here, this is done by defining defining just a single variable, which is a guest memory, and the guest memory is a function from guest and address to value, and it is initially empty, and then we have a single event called write with three parameters: a guest, an address, and a value. And G is a guest, A is an address of this guest, V is a value, and we just write the pair with the pair GA. We write in the memory. We write the value V. So this is just very, very simple. Okay, so now the next step is to go on to slightly step by step introduce the notion of the hypervisor. We have now a second context, and that context is defining the slat of each guest connecting a guest address to an IPA to host address PA. And both IPA and PA are addresses. So that corresponds to your question. You see that the slat here is just an injective function from a pair guest address to another address. So I do not define at all this sort of thing at the beginning. So, and it is a constant because you remember it has been defined. It has been entirely defined at boot time. So everything that is defined at boot time, from the point of view of this, are constant. And so now we go into machine M1. So machine M1 is seeing now this context C1, and the context C1 was itself extending context C0. And now we data refine the guest memory. So the guest memory has disappeared from the variable here, and we have only the host memory. So we start doing things at this level now. We have here a gluing invariant that is gluing the guest memory to the host memory, and it is very simple. It is just the functional composition between the slat and the host memory. And because the slat is injective, all the parts that are in the host memory for a certain guest are different from that of other guests. And so the transformation here is very simple. Rather than writing, I can show both of them. I can show here the abstraction. So the abstraction was guest memory of GA, and now we have host memory of slat of GA. And because we have the gluing invariant guest memory is slat composed with host mem that you see here, so the proof will not be very difficult. Okay, so this is it for M1. So now we go to M2. So M2 is doing the following. In this second refinement, what we do is we introduce the various core. We introduce now, we have shared the memory, and now we are going to introduce these people. So we introduce the various core, and again, we have an abstract connection between partial injective connection, partial because we might have more guests than cores in the hypervisor. And so this is the scheduling precisely is going to assign a guest to a processor, to a physical processor. And as I say here, we also define the scheduler. This is done through another context here, and that other context is defining. I'm not sure. Maybe not. Let me have a look at. So we are here. M2. Yeah, M2. Okay. So this one. Yeah, it uses C3, and C3 is defining C3 is defining the set of core, of course, and we have here the set of core. It's an abstract set defining all the cores that are used, all the cores that are here that are used in the hypervisor, and now we have M2. So M2 is defining something, a new variable called core to guest. It's a partial injection again between core and guest, and in fact the CPU of the guest, because we are supposed that the guest are a uniprocessor. And we have, again here, a little modification of write, which becomes fatter and fatter. And now this is host mem of guest light, of core to guest, of C and A. And now the guest has disappeared from the write operation, from the parameter, and it is replaced by C, and the connection is the G of the previous abstraction is core to guest of C. And of course, this is done only if the guest is not sleeping. And then if the guest is not sleeping, then C is in a domain of core to guest. And now we go to M3. So M3 is doing the following. In this third refinement, we are going now to disconnect the guest from the slat. Before we had a direct connection between the guest and the slat, and now we are going to introduce this notion, this base address here. So we slightly enter into this, and we connect now. We connect now the guest, each guest with a base address of its slat, and also we introduce a base register in each CPU. It's a hardware register in each CPU, and when the scheduling occurs, what happens is that the base register, the base physical register of this CPU is assigned the address of the corresponding guest that is now going to be executed on that CPU. And that gives us a little more complication for these things. Host mem, still host mem, of course, slat register of C. And now we introduce for the first time the scheduling. And precisely in the scheduling, this is what I told you, in the slat register becomes the guest slat address of G. So guest slat address of G is the address that is here. It is a table that is again defined at boot time for each guest. And this register, now this is a physical register. This physical register is assigned at schedule time. So now we have connected this guest through the address of its slat, and it's put here in this register. Okay, so now we are ready to go here. And now what we're going to do is to implement the slat for now is just a big table that is here with this base address at the beginning. But that's not the way it is, because now we have these trees. And what we have to prove, and it is very important, because we say, and it's absolutely fundamental, that the slat was injective. So the slat was a connection between IPA and PA, PID and PID and PA. And we have to prove now that the entire thing is in fact implementing an injective. So it's still a one-to-one. So here we enter into some things that are a little more complex. And I have to introduce, of course, this sort of thing. And we want to do it still at an abstract level. We do not want to introduce the bits, but we just want to introduce this sort of thing. So this is defined, I think, in this. No, this is defined in the next one. So this is defined here. So this is a structure of the slat as a three-level tree, and we are going now to decompose our address. So we have a notion of IPA and a notion of PA, and these are all page addresses. And now we define this, but rather than defining this as 32 bits, we just define some projection function, IPA1, IPA2, IPA3, and we call them 10 bits, and 12 bits. Okay, we do not go into the real bits. There is no point in doing this. And of course, we have to do some more axiomatization. And the first one, which is quite important, is that this tree projection, IPA1, IPA2, IPA3, defines unambiguously an IPA. So if you have two IPAs and they have exactly the same projection, they are the same. Okay. And now I define the base. The base is a page, is a bunch of page address. These are all the bases for all the guests. And now I define page address L2, which corresponds to this, and page address L3, which corresponds to this. And between the base, the base, and between the page address L2 and the page address L3, they form a partition of the page addresses. So the fact that they are a partition means that their union of the tree is exactly the page address, but they do not their intersection is empty. So you see what I'm constructing here, little by little, is precisely this notion that will make the basic theorem that this implementation of the slat is indeed an injective function. And now I define the word content for a page address for 10 bits, and the byte content for the 12 bits So this corresponds to this, a byte, and to this, a word. And then there are, I'm not going to enter more too carefully. Here I have a number of technical theorems, but the final theorem, which is here, the fundamental theorem, which is proved, which has been proved, is that the slat is injective. If we have slat B I1 equals slat B I2, so if the correspondence is the same, then I1 is equal to I2. So I've proved by being very carefully here with those injection that this entire thing here corresponds to a one-to-one correspondence between this and this. And so this is done in the context, and now we go on to the this machine M4. So well, by the way, we do not go immediately into this structure. We introduce a TLB, the famous TLB. You remember the associative memory. So now I am going to say that we have sometimes this short circuit between a PID and this. So this is described here, so in fact the write operation is divided into write 1 and write 2. In write 1, the address is not in the domain of the TLB. Therefore, we have to walk, we have to do painfully the work. But at the end of it, when we find it, we update the TLB by evicting a certain member of the TLB. And write 2 is also a refinement of write. And write 2 here has got this guard here that A is in the domain of the TLB. Therefore, we just use directly the TLB. And the scheduling is not different. And now we go into Hypervisor, the last one. And the last one defines we are going now to split the event. This is very classical in Event-B refinement. We have an event which is something that is doing things in no time, and now we are cutting it into pieces. And the event write 1 which was the one that was walking through this structure, is now going to be divided into write 1 0, write 1 1, and write 1 2, because this is not done atomically anymore. In the abstraction that was done atomically, but now we have 3 steps, and this is defined. And in between the steps, the things are stored into supposedly some hardware register. And this is what is done here. So we have write 1 0, which writes things into some register. It goes from here to here by taking the upper part of the memory, sorry, of the physical of the address, of the intermediate address, and then write 1 1 and write 1 2, and write 2, which was using the slat, is not modified. And now we go on to the last one. Which is oh no, this was the last one. This was the last one. Okay, so this is the end of it, and so all the proofs have been done. Here is the statistics of that we have for this. So you see, it's not small. We had 176 proofs for proving all that. All the proof for maintenance of invariant, and all the theorems have been generated by a tool called the proof obligation generator. And but all automatic, 69 automatic, except 9 of them where I had to do an interactive proof. So an interactive proof is just giving some clue to the automatic prover so that he can finish the discharging. I have not tried to optimize things, so it might be better, but I've tried to do the things as it is. So this is finished for the interrupt. for the memory, we have a certain status. It's not the final one, but you see, and what is important to see here in those events is that some events corresponding to the hardware, some events corresponding to what the hypervisor does, and actually this is not completely clear-cut what is done by the future software of the hypervisor and what is done by the hardware of the hypervisor. By the way, the machine with a slat makes things far more convenient for the virtualization. So now we're going to the interrupt.
Yeah, or should we skip to the conclusions, or do you want
Yeah,
to
maybe
show
we
one
should
slide
go to the conclusion directly. If you are interested, these slides could be given to you. Here, just let me give you the final stuff for the hypervisor, for the interrupt. We have 205 total proof, and here we have a little more of proof done manually. We have 35 of them are done manually, because in the last one there are 22 of them. So I have no time enough to do it, but we have written the requirement document, so this is available, and we have and those slides are available. Okay, so let's conclude now. Oh yeah. Yeah.
Great. All right. So in conclusion, so what you've seen is the flavor of the way that the top-down development is done using a tool like Event-B, and some common themes are that details are introduced gradually, and so you need to know only so many things. So, for example, with the bits, you don't need to know exactly that they're stored in bits. You can work at a more abstract level, and that's very convenient. If you start from the code, you have all of the concrete details to look at right away, and then you'd like to try to abstract from there, and that seems to be much harder. So in what you've seen, we also have the interrupt part, which looks similar in flavor to the development of the memory manager, but there are many more things that are missing. So the model still is quite abstract. So we need to continue going down into more concrete levels so that we can eventually get to code that could actually be executed. You saw that in the refinement, you get more and more events. So as you get more and more events, at some point, the final thing is going to have some events being executed by hardware, some of them executed by software. And in the process, there have been many things that we have puzzled over, where we have to sort of make up our own rules for, I mean, what is hardware, what's software, and then we've consulted with experts, and we say, aha, well, maybe we really should move this. This is really a hardware kind of thing, and oh, there's the such and such a piece of hardware like the TLB or whatever that we should consider in between. But the idea in the end is that when you look at each one of the events, you can see that this event is one of the software instructions that you can execute in the machine, or this is a task, something that is performed by the hardware. And when we get to that point, then one can actually get the code generation is the idea for those software pieces. And of course, many of those events at the end are going to be whatever the host OS is doing, and we don't, for the most part, we're independent of. Well, we want to be completely independent of what the host OS, what the guest OSs are doing. In the end, also, when we would get to that point, we also have to go back to the requirements documents to check off those each one to make sure that we are really living up to what that document says. You can think of the requirements document as a contract between the developers and users of a system, and we're trying to get those right. And there are some other pieces that you would want to have in a realistic hypervisor, like timers, for example, that are missing from our model. So from the standpoint of trying to develop this as a Gedanken experiment, or I mean, these refinements have been done before, but we're developing something for as a something where we can see all the pieces come together, and and the tooling is there. I mean, we have expertise in our group in developing tools and automatic reasoning systems. So maybe there are some things that can be done there as well for making things in a process like this more automatic. So with that, we'll open up for questions. Thank you very much. Yes.
So where do the specifics of the instruction set architecture come into the picture?
So right. So so what would happen is that there's some event that models the operations of each guest OS. So what we saw in the memory model here, it's only one instruction. That is, we're now looking at it as if each guest OS is just doing write instructions. But there would also be skip instructions. That is, things that the guest OS would do that are of no concern to us. That is, they can do whatever they want. And what we need to show at some point is that if we then have real instructions of a piece of hardware of a processor, we need to show that those instructions are correct refinements of skip. In other words, they don't interfere with the operation of the hypervisor.
Right, but if a CPU has specific support for hypervisors,
right,
where does that come into in the models?
That's right. So imagine
AMD and Intel architectures have specific instructions.
So slot.
Right. So take an operation.
The slat is
done by hardware. So at this model, they just know that there's a slat. They don't know who does it.
So think of it this way: in that skip event that needs to be refined by instructions that would be done executed by each guest. If the guest attempted an operation that can only be done by the hypervisor, that is, you have to put the processor in the hypervisor mode to be able to execute, then what we would need to do is simulate that. That is, when doing that refinement, we need to model that the execution, the hardware's execution of that instruction by giving a trap. Doing something that prevents the guest from mucking with, for example, the slat, or mucking with directly with the physical addresses. A guest should only be allowed to muck with the intermediate physical addresses.
The set n was abstract, or was it natural numbers? The set n was abstract, so it was finite set.
Yeah.
No, wait, the n that you saw in the...
In the what?
That is used for the addresses.
Right.
Yeah.
Mm-hmm.
Yeah.
Do you have any
At the
feedback?
beginning, it was a set of natural numbers, but then I tried to abstract. There is no point in taking natural numbers.
But that would also be, that wouldn't correspond to it.
Yeah. Later there will be some refinement, and then.
But yeah, so it's possible at that point. So if you use natural numbers and refined from that, and axiomatized that you had injective functions, where something you had a domain of natural numbers.
So the way to...
It wouldn't correspond to any implementation.
So if you have an abstract set that lives in the context, then what you're doing is you're doing a development, a refinement that is parametric in what those are. Right.
Yeah. Oh no. So no, it will not be the natural number. It will be a finite portion. Yeah. Sure.
Yeah, Mike.
Do you have any feedback from the Hypervisor project or the VCC verification of it that, like, the kinds of things that you were doing here, are these where errors were found in the Hypervisor, or would such a development have prevented errors?
We don't have such feedback. I mean, we've right. That is, I mean, right. You can check with that. Maybe Mihal knows more. But the feedback that, I mean, we have consulted with two of the people who were involved in that verification. That is, in verifying the Hyper-V to get a sense of what sort of models should we have, what kind of hardware can we expect, and things like that. But yeah, I don't know. You'd have to check with them to see what sort of errors, whatever they discovered. But one thing that I should have said is that the reason that the hypervisor seems like such a good thing to do an experiment like this with is that many pieces of software, dancing clowns on web pages, for example, I mean, we don't really care if they're really correct or not. But here, the hypervisor is something that you really care that the machines are independent. And furthermore, if you try to debug it with standard, techniques, you're operating at such a low level that it's very difficult to try to understand at that level, if you have something that goes wrong. So therefore, trying to use a technique that is designed to start from abstractions and get down to correct things is, seems worthwhile here. And you notice that, after these, 5 weeks now, we don't have any code. It's not there yet. Whereas if you were to do it the traditional way, you probably would have written, code certainly by now. So, right.
You probably just didn't push that button on the toolbar.
All code is vacuously correct.
Yeah. So, Jason, did you also have a question?
Yeah, so I was wondering where the virtual address translation sits. Is that before or after?
You mean so you're thinking each guest operating system probably has a bunch of processes running. And when...
Virtualization, right?
That's right.
So that sits before...
Right. So that sits before. So all of the address that we being the hypervisor would get is already a request for a particular intermediate physical address. So what each guest operating system presumably would do is it would have virtual addresses that it gives to each of its processes, and it maps them, in fact, using page tables and TLBs, very similar to what we have here, but maps that into an intermediate physical address.
Yes, but my other question is that's usually done directly by the hardware. So the
Yep.
hardware will
Yep,
do
that's
that.
right.
So
That's
so
correct.
you're able to trap it after the hardware does the lookup?
Right. So all of that happens in the guest mode. And then that whole process, in the end, comes up with one IPA, one intermediate physical address, and that's what we get. So we don't actually care. A guest OS could decide to not use that virtualization mechanism or come up with its IPAs in any kind of way, but of course the most likely would be that it would do it in just that way.
So there's a second...
Well, that's why it's called SLAP, second level.
Yeah, so it's the second level one, and then there's... I can't imagine that would be fast at all unless there was some specialized hardware also doing that process.
You're right. Yeah. So there, we would assume hardware like that, and actually we've gone through and thought much about, also how that is. But for our modeling, it plays no role. Well, actually, that's not right. In the end, it will play a role because when we would have to take something like a skip action or something that is done by each guest, we need to be able to refine it into what the hardware does for those sorts of things. But as far as all of these things, the translation from IPAs to PAs, we don't care how the guest comes up with its IPAs.
And in each TPU there are two TLB. That is the TLB for the guest and a TLB for the hypervisor. So the TLB for the guest, we don't care. This is the business of the guest. And at the end of the TLB of the guest maps a virtual address of the guest to an IPA. Mm-hmm. And then that IPA, and then the guest wants to write directly to this IPA, and this is this part that is trapped by the hypervisor.
So this is developed specifically for hardware that has the ability to trap the second level.
That's right. Exactly. Yeah. We're assuming that there's such a SLAT, right?
That's not a software.
Right. You could refine it
You have
as
to
software.
believe that you've got the chance to get in there and intercept it.
Right. Yeah, that's
hardware.
That's what I'm saying. Is you have to know that you can trap it after otherwise you would have to simulate every.
So what the real the Hyper-V hypervisor is doing, it was simulating SLAP on its own by messing up with the normal first level address translation, and that was essentially most of what hypervisor was doing. That was the most complicated stuff, and that's also where they found the bugs. And here it's kind of just taken care by the hardware.
Right. Yeah. So and we also, by the way, we didn't look at the details in this talk about the interrupts, but the interrupts see very similar things that because of the virtualization that's going on, that the hypervisor gets the physical interrupts. And it will then do things to mark them as being active, that is, that they're being handled, and then forwards them onto the virtualization hardware for that goes to each guest. And at that point, what the guest does, if the guest I mean, take that interrupt, or what it will do in its interrupt processing routine, whatever. We don't care. We know, I mean, a few things. For example, like there are a bunch of priorities that such guests can set. And when you set those priorities, then you can get a stack of interrupts. So we're modeling that, and then the guests are supposed to then peel off these things I mean, pop them in the same order, in the opposite order from the way that they were pushed. So we're guessing that, I mean, the hardware would trap any violations to such a thing. But again, most of that is just independent of what the hypervisor does. The hypervisor just tries to simulate the physical pieces of hardware in a virtualized way to each guest. Right. By the way, right, I should have said here also the initialization. The one thing that we have not looked at is, I mean, how do you initialize all of these tables and the interrupt maps and so forth? And there, our understanding is that there's something, I mean, in the BIOS or something that would tell the hypervisor how to set things up. But we have not looked at that. That needs to be done. That's a missing piece.
One thing what is very important in the separation of future software events and hardware events, the software event will give rise to code, but the hardware events are important too, because we have to check now that the physical hardware corresponds to the model we've done for it. Mm-hmm. Right. And so it's a way of and we have to do things. We have to dig into the documentation or to dig into the real physical hardware to see whether our events are, because our software will be correct with regard to those physical events corresponding to the hardware. Now, if the hardware is doing something different, then we'll have some problem, of course. Mm-hmm. So those events are also important. Okay, and I think even more going more further, it could be used also by the hardware people. They could formalize the future hardware and then implement it in the circuits.
All right. Anything else? All right. Thanks very much.
Thank you.